So in this video we will talk about the first operating modes of a synchronous machine. It is like the standalone generator. Okay, so it is like the usual case where you have a single diesel generator, okay, usually, and you just supply the load and you are not connected to the electric grid. So it will be, something like that. You will have I don't know, some here, I don't know if you can see, I don't know if you can see, there's here a synchronous machine and it is probably supplying a load, and that synchronous machine is connected to a prime mover or a diesel engine, internal combustion engine. So it supplies the mechanical energy for your system. Or I don't know, maybe you set up a small micro hydro generator which you have the energy from a flowing of water, and you can supply your own electricity, but that is not connected to the grid. Okay, so here again I think it's a cold start, so generating lots of smokes. Anyway, that's at the end of the day, that is where the power for your synchronous generator, where the mechanical power is coming from. So if you look at the block diagram, so it will be something like that. You have a prime mover, okay, so that is your generator. Okay, so here you supply some torque and you supply some speed. So the prime mover, I don't know, can be a diesel engine, okay, like internal combustion engine, or it can be a hydro turbine, or it can be a wind turbine, I don't know, it can be a, I don't know, bicycle, any kind of system that you can generate some mechanical energy, and that energy now connected to the your generator. So this is your synchronous machine, but it is operating as a generator. Okay, so you have 3 phase coming from your system, and you have your voltage and current. And again, let me make the connections. So you can have a load, a 3-phase load, and it can be connected to that electrical load. Okay, so you have V phase and that kind of system. So again, that thing controls the power flow. Power flow is in that direction, and for load we want to keep voltage and frequency constant. So that is your problem. Okay, if the load increases, then you draw more current, and if that power is larger than your mechanical power, then the system can slow down, or vice versa. Or if, I don't know, there are maybe leading or lagging power factor devices, that will affect our terminal voltage, as we have seen in the previous video. So our challenge is to keep the terminal voltage constant regardless of our load conditions, and we want to keep the frequency of the electricity generated constant, because our devices are designed for either 50 Hertz or 60 Hertz in US or Japan, or that few countries like that, but they want more or less a constant frequency, right? So we want to keep those things. But in the standalone generation, you can have a resistive load, or lagging load, leading load, that can change with respect to what the consumers are using. But anyway, just as a to start with, let's assume the unity power factor case. So assume now the field current and speed is kept constant, and somehow we just pump. We will talk about that one as well, but we just send enough fuel or water or whatever to keep the frequency and the speed constant. But let's look at what happens to the voltage as we increase the load. So here let me draw it again. So you have or let me draw the single phase. Again, this is a three-phase system, but I am drawing a single phase equivalent circuit. And again, let's ignore the array for this case, and we have our load. Okay, so this is our VT, this is our I phase, this is JXS, and what will happen if I phase is increased? Okay, and IF, let's say IF is constant. So if IF is constant, the magnitude of EF will be constant as well, right? So what will happen if I increase the phase current? So speed is constant, IF is kept constant, and the magnitude of EF is constant. So here you see the animation, you see the phasors. So at first I have the EA or I have the current here, right? I have the current here, and it is in phase with my phase voltage. So this was my initial phasor. So then in the prime versions, it is the second, the increased current. The current increases, and if the current increases, so does JXSIA. But the thing is, if I keep IF constant, EF will be constant. I am not controlling the load angle yet, but I know the field current is proportional with EF, so it will stay constant. So the only place that phasor can move, okay, the only place that can phasor move is just on a circle. Okay, so that is the circle that EF is moving up and down. So in this case, EA can move in the constant direction. So again, remember, in our system, there's nothing that defines that phase voltage. It is not connected to the electric grid. Like, it doesn't have to be 230 volts all the time. So it is completely independent, and the only thing that defines my terminal voltage is EF magnitude, okay, then the difference between that one. So again, in the previous video, I always draw like VT as it is the reference and it is there, but in this case, like, EF is the defined vector here, current is the defined vector, and then we have the terminal voltage with respect to magnitudes of these two parameters. So if you think from that point, it should be clear that as I increase the load, the magnitude of terminal voltage drops. So it is like a transformer, okay, you can think like that. So it is as a transformer working at unity power factor, and as the load increases, the output voltage actually reduces, and you can see that. Okay, so there is like a voltage regulation problem, and actually you can see more animations in that link. Okay, so with the, let's have a look at the same thing with the lagging power factor. So this was the unity power factor, and here this is the lagging power factor. So again, initially I have that configuration. I have the IA here, I have the EA here, and as the current increases, okay, again my EF can only move along that circle because the radius is constant, because radius now, and this is the case with what happens if we don't change anything at all. Okay, so we just keep the IF constant, so EA can move along that circle, and as you increase the load, as that current increases, so there are two things that is happening. So actually we had the same thing in the previous case, but I forgot to mention. So as you increase the load, okay, so yes, terminal voltage gets smaller, but actually your load angle increases. So in the initial version you have a load angle like that much, and as you increase the current, then you have an increased load angle. So that is because the fact that now you are drawing more power from the generator, and that power has to come from somewhere, and that power is coming from the mechanical energy, so that is increasing the load angle. And the same thing is happening with the lagging power factor here. As you increase the load, okay, the power factor, the load angle has increased, okay, and also the magnitude of terminal voltage is reduced from that point to that point. So the decrease in the VT is actually, you know, if you just look at that value and that value, the reduction has increased. So it is really similar to what we did with the transformers in the first semester. Remember, voltage regulation was worse with the lagging power factor, it was negative, and with unity power factor it was still negative, so the output voltage was reducing with increased load. So let's have a look at the case with a leading power factor. So if you have, again, it is not the case for every leading power factor, but if you have quite a large angle between your terminal voltage and current, okay, so you have again the current here, and this is your initial phasor, and as you increase the current, again in this one the field current is not changed, so the magnitude of EF cannot change, so it can only move along that circle. So the only solution to your problem with that magnitude and that current is that point here, and at that point, as you increase the load, now the terminal voltage is slightly increases. Okay, so that was the case again if you remember the transformers. If you have enough leading power factor, the voltage at a transformer secondary can go up with increasing the voltage. So that is not the case in a DC system, right? So you draw more current, and because of the resistive values, so you will have less and less voltage. But in AC systems, actually the output voltage can increase in leading power factor systems. So what you have to do is to again regulate that voltage. If you don't do anything, if you just keep the field current same, so you can define a voltage regulation. It is completely the same thing with transformer voltage regulation. You can define the magnitude of the voltage at no load, which is equal to EF. So again, remember, if you don't draw any current at all, then the EF will be equal to your terminal voltage, and then you subtract it the full load, okay, then you divide it by the rated load or full load voltage. Okay, so again for unity and lagging power factors you have negative voltage regulation, so that means output voltage tends to decrease as you increase the load. For leading power factors, again, not for every leading power factor, but if it is, you know, significantly leading, then you can have a negative voltage regulation. Negative voltage regulation means that full load voltage will be larger than no load voltage. So if you subtract it, this one from the no load voltage, you will have a negative value. So that means your output voltage tends to go up even if you increase the load. So actually we can use it to our advantage. So you can choose the best loading, best power factor that affects the output voltage at minimum. Okay, but again, for most of the time, you know, this is not the case. You don't have any direct control on the power factor. I don't know, the user can connect the motor, can connect the kettle, can connect a computer, I don't know, can connect a light bulb in that standalone generator system. What you have to do is you need to measure the output voltage and you need to compensate for that voltage drops. And how we can do that? You can do that by controlling the field current. Okay, so you can adjust the field current. Okay, so here, so you can, for example, if the voltage is dropping, what you can do is you can increase the field current and the magnitude of EF goes even larger values, then you can still get the identical voltage regardless of the load condition. Okay, so you can achieve a constant VT, and these are, you know, in practical systems they are done with AVR systems, and AVR is short for automatic voltage regulator systems, and usually they have, you know, that kind of systems, and in that one you have connections for the, you know, phasors and that kind of things, one of the line voltage and neutral voltage, that kind of things. So F plus is the plus polarity or positive side of the field current, negative is the current, negative terminal of the field current. So you can control the amount of field current. So at the end of the day, remember, it is a rotor with some field winding, so it is working as an electromagnet. So you can control how much flux density is generated by controlling the field current, and by doing that you can control the magnitude of EF, and by controlling the magnitude of EF you can control the output voltage. Okay, and there's also another thing that we need to control. It is the frequency. Okay, so I don't know if you can see that device. Okay, so that is a really fundamental device. I think this is one of the original machines from Watt's steam engines, and I will show you a video shortly. So what does that device do? So this is, again, this is called a speed governor. Okay, so the idea is like really old, but it is really simple device. So this is to regulate the rotating speed of a steam engine. So the operation principle is simple. As it starts rotating faster and faster with the centrifugal forces, you know, those walls will want to go apart, and with that lever they are controlling a valve, and as they spin faster and faster they close that valve, and that valve is controlling how much steam is sent to that machine. And actually if it goes slower and slower, then those balls here will go to the vertical position, and then it will give full throttle. So these are called the speed governor. Okay, speed governor, and it is nothing but a, you know, centrifugal flywheel or flyball system, works as a speed controller, and it's full analog. You know, it's like a proportional controller. You know, the difference with that one is controlling the valve, but they are working quite nicely, and I have a video here. So this is again the original steam engines from Watt's system, James Watt. So here, I don't know if you can see, here you can see the speed governor. So rotating, and here, okay, here it is the speed governor itself. It's rotating and it is adjusting the amount of steam, so you can rotate the synchronous machine, you know, connected to the other end of that steam engine at this constant speed. And actually we are using more or less the same technology, so you can click on that link to see how a system operates in a let's say natural gas power plant. In a natural gas power plant, what you have is large ovens or furnaces. So you heat the water and you generate some steam, and that steam is sent to some turbines to rotate a synchronous generator. And the amount of steam sent to that device is more or less, you know, it can be a digital system, but the idea is same. It can be controlled with a similar device. So speed control gives us a constant frequency, constant let's say 50 hertz output voltage frequency. So at the end of the day, if you look at the whole system, it is something like this. So let's have a look at, let's start from the electrical generator. So you have electric generator here. So it generates three-phase voltage and currents. So you have a voltage sensor and you regulate that one. So there's a set point. So this is for a large generator, 13.8 kilovolts, 13,000 volts. There's a set value. And then you have the AVR, automatic voltage regulator. Then it controls the excitation system, and excitation system controls the output voltage by changing the EF. So that part ensures the output terminal voltage is constant. Then you have another control loop for the prime mover. Again, here it is a diesel engine. It can be a hydroelectric power plant. It can be a wind turbine. I don't know. It can be like diesel engine, steam engine. It can be a nuclear power plant. At the end of the day, there is some steams getting into that place. So you measure the speed, and remember the rotational speed is again proportional with the output frequency of the generated voltage. So if that frequency goes down, you need to increase that speed, and there's a set point again. This is for that system, and there's a speed governor, like we have seen. It can be an algorithm, it can be a mechanical device, whatever. So then you just control the fuel, you just control the steam, or you can just control the like the flaps of the hydraulic dam. So you let more water to come into your turbine. At the end of the day, this is for a diesel engine. So you control the fuel, and then fuel goes to injection pump, and that diesel engine produces more mechanical power, and that it accelerates the generator until it comes to the set value. So there's a speed loop which ensures the frequency control, and there's another loop for voltage control. Okay, so that is the operation, the standalone operation of a synchronous machine. Okay, thank you.